All right, now you're having too much fun. So basically, I'll start the next part, which is the filter design to IIR systems. But before that one, remember to fill those forms. Those are very important forms to fill that basically will be used for the future generations to get what they are basically entitled to when you or your the followers will be getting into the summer jobs. So filling those information that helps you next year and the rest of the engineering students beyond. Okay, so let's see, does this one work? No, it doesn't. So IIR filters. So basically now we are talking about infinite impulse response systems, which means that the filter always have somewhat linear, non-linear phase. So it's never linear phase filter. So basically if you need a linear phase response, then basically the only way to get it is FIR, which has its limitations. But anyways, however, these are basically better amplitude response with lower number of calculations. So those, in that sense, it's more effective if you are interested only on the amplitude response. For example, on audio. Audio is excellent example where you almost never use any FIR filters unless it's a special need. For example, of course, sampling of the that easiest to do with the FIR, but otherwise you would do it with the IIR systems for several reasons. But anyway, so and then whenever you need high Q factor, meaning narrow bandwidth the filters, then the IIR is your answer. I should actually show a couple of things why that is on the white screen there. Good. So the black. Remember the complex unit circle. When you have a FIR filters, the only way to actually control the system amplitude response is with the zeros. When you put the zeros on the unit circle, you will get also the 0 points on the amplitude response like that. And then basically if you put the zeros close to unit circle but not exactly, you basically can do a kind of attenuation on passband to make it flat. So that could be, no, that's not correct. Let's put one more. No, it could be closer. Anyway, so basically you are putting some zeros to push the amplitude response and some points the down. Okay, and that's the only way to get it, and you still kind of get quite a lot of the stop band the feed through. Anyways, when you're taking a the opposite way on the pass band, you can still have the same the stop band notches there, but for example put only a couple of these poles close to the unit circle, so basically you get more gain, but at the same way you get, say, better stop band attenuation. with fewer calculation points. It's just quite obvious when you're taking a look at this, since every one of these actually requires one multiply accumulation. It's basically the same as, a number of zeros and poles is the same as the number of calculations plus one. Okay. So better efficacy with the less calculations. That's the IIR, why we are using IIR filters. All right. So back to this one. So the only kind of fallback on the IIR filter design is that these design methods are quite complex. There's only one design you can do by pen and paper. The rest of the design methods actually require at least some tables, transformation tables. But anyways, those are the 4 most common methods. So there's the digital filters, actually the first digital filters on the IIR digital filter were based on analog counterparts. So those are the classical analog filters like Butterworth, Chebyshev, elliptic, which probably you haven't heard of them. Okay, but there are some analog filters based on negative feedback and some let's see, Sallen-Key structures on operational amplifier circuits. Okay, and there you can make it kind of sample the system. Where you have an analog system, you can always make a model of the analog system, and bilinear transformation is one method of making a such kind of transformation. And where basically if you have an analog system, let's move it back here. There we go. So on analog system, you don't have the C plane, but you have S plane. Okay, that's the S plane. This is the where the poles should be. That's the stable region, and this is unstable. Here, the same things on the sampled system. You have stable region and unstable. So, and there, while the digital frequencies are on the unit circle, then this on S plane, these analog frequencies are actually on the J dimension. So that's where the J omega is. Here we had the point E to J omega. Okay, digital frequency. Stable, and there we have the system, for example, like that. That will be Butterworth design. Yep, I know it. Okay, basically this bilinear transformation is the way to transform these pole locations which are on the analog domain certain way that they actually fit into the this Z plane, and there's only a simple trick with you have H of S. You basically move that one to H of S equals 2. I think it was 2 over T. Let's see. Oops. 2 over TS, yes. Just a calculation, 2 over TS. Z minus 1. Z plus 1. Okay. So actually, when you look at this one, you can kind of think of what is the frequency when Z is minus 1, the analog frequency would be either minus or plus infinity. So in one sense you take this j omega axis from infinity and minus infinity, turn it into the unit circle. Okay. Long arms. Yeah. And the basically it maps these frequencies here. If you have somewhat linear scale here, it will map that one in very unlinear manner on the this unit circle. Okay, but it's straightforward substitution of oops like that to get the transfer function from analog transfer function to digital. And it actually works with any system which has an analog transfer function, any continuous time system, pendulums or motors or whatever you have. You just bilinear transform that one and you have the digital model of the system. Okay. And yes, if you have a first order system on analog domain, then you get also first order system on digital domain. It doesn't affect on the amount of those zeros and poles. Well, poles yes, but zeros no. No, the other way around. It adds some zeros. So the order number doesn't change, but it warps the frequency scale quite drastically. Anyhow, if you have a say natural system, usually the order numbers are quite small on real natural system, up to say 8 or something like that. So you get easily a IIR system out of by using the bilinear transformation. Simple, effective, warps the frequency space. All right, that's one way to basically do the trick. The second one is kind of, it has a fancy name, it's parametric modeling. All right, so any dynamic system, you can actually write a differential equation that describes the behavior of the system. Your physics teacher will tell you more if you ask, and he'll be very surprised that you asked. Okay. But anyways, that's basically quite simple. On this, well, that's the first method. The second method here. Parametric modeling. So we have, for example, second order. Well, let's see, ax dot dot plus bx dot plus cx plus some factor, or actually that is usually like that, is 0. That's a differential equation of second order showing, for example, how pendulum swings. Okay, that could be just, well, that's basically acceleration, that's speed, that's a local position. Okay, then those parameters just change, and that's the time derivative dx over dt, and that's squared, or d squared, so second time derivative. But anyways, there's also this parametric modeling, quite simple. You just replace dx over dt by delta x over delta t. All right, so it's simple sampling without any worries about the consequences. And delta x is just xn minus xn minus 1, so it's just a difference between two subsequent numbers, and this is, well, TS, sampling time. Simple linear interpolation of the difference equation. Depending on the sample time, if the sample time is short enough and the system hasn't changed much in between those time steps, then this is just fine. Okay, however, the problem of that one is, while the good point is that the frequency scale is actually still linear, it's still exactly those times points, it's just sampled time points. But the problem actually comes on the fact that, okay, let's see where I'm looking for, there we go. Think of the frequency space. On continuum time space, we have, for example, this system frequency response is something like that. It continues from minus infinity to infinity. Okay, but when we sample the system, what happens to that part of the spectrum? It aliases. We do the same aliasing error as we did on the very first lecture. So basically this one aliases here, and you'll get the aliased spectrum at the top of this one. Okay, if we have fast enough sampling rate compared to this possible signal changes, it means that this is negligible. Okay, and then it works since there's nothing to alias. All right. Third method. Yes.
Possible to just create that with the really high sampling frequency first, and
yep.
then you have discretized it and you filter it again.
Yes. Yes. Decimate it.
Yeah.
Yep. Drop the do some digital filtering and stuff like that, and drop the sampling rate. The same as the this sigma delta A to D converter is actually doing. It's 1-bit conversion at the beginning. This A to D conversion for audio. All right. And then third one, direct design. It takes some balls to do it. Okay. So this would be direct design, meaning that you just start putting the zeros and poles on the positions you think they would be from the first place. Then you start wiggling these parameters a little bit to match exactly what's supposed to be the your filter design. Okay, not recommended unless you are doing just one single simple design, which is back actually the I think we have that one on the exercise. So you can do the direct design only on one filter, and good luck with the other ones. If we put a 0 here on that omega 0 angular frequency, it means that it basically on that frequency we have 0 or infinite attenuation. All right. And complex conjugate pair, of course. And then we basically just take the these poles and put them close range at the same angle, meaning that we are also bringing some magnification, amplification of the signal here on the same frequency. So originally the system would be FIR and look like this. But we take the poles from the origin and push them in nearby. Basically what it does, it makes the other part of this amplitude response more or less flat. Okay. And even this width of the filter can be adjusted quite easily. Well, half width. Half width is exactly the same as that one. The distance to the unit circle. Okay, how come? Oh. If we are here, remember the amplitude response? It's basically the product of e to j omega to 0 point times e to j omega minus 0.001, okay, divided by e to j omega minus pole 0 times e to j omega minus pole 1. All right. If you are somewhere in here, in far away location, basically all of these distances are just about the same. So distance from, for example, from here to there and there, it's about the same as, well, distances here and here are the same, as well as those distances about same. So if we are far away, then it's almost unity gain. And when we are getting closer, let's expand it a little bit. Okay, that's the unit circle, pole 0, that's the angle omega. All right, and that was the distance A. Think of the distance A here. This point here is basically the same as that one. Right. Well, yes. That distance. So this is same as that one. That's about the square, and magically this distance, when you're thinking again these two, it's about square root of 2 times A. So in here we have that distance is square root, that one is about A, and this distance is square root 2 times A, meaning it's 1 over square root of 2, which is minus 3 dB. Okay. So basically this distance is roughly the same as the half width of the stop band. There, simple. And that's the only filter, IIR filter, I recommend anyone to design by hand. But then also this fourth method, optimized methods. Now we are talking about something that someone has already done for us, and it's there are plenty of research done on this field because there's a big need for IIR filter design. Okay, meaning that there are already tools to do optimized filters. Some of them are actually commercial, but well, MATLAB has most of the say non-commercial. You just need to have that expensive license from MATLAB. Or Octave also have some of these methods already there, even the optimized ones. All right, and that's the bandstop notch. The classical filters. I mentioned the classical filters on this bilinear transformation. Fundamentally, classical filters are well, those three filters are the most used filters. There's also the fourth one, which is Bessel filter. Well, it's nearly linear phase response, but when you do the bilinear transformation, it's nothing like that anymore. So only those three filters are actually recommended for, say, any use for the starting point. So fundamentally, the Butterworth, that's maximally flat passband, meaning that it's basically unity gain, and say quite simple to design. Then the second one, well, yeah, that was the let's see, blue, yes, blue line there, Butterworth filter, and that's what happens when you do the bilinear transformation to the analog filter. Okay. Chebyshev type 1 actually means that it has equal ripple on passband and high attenuation of stopband. There's also Chebyshev type 2, but those are not practical on analog filters, so basically it's no use to transform those to digital domain either. But anyways, the Chebyshev 1, which is the green, has a, say, it's quite fast response and goes very deep into the on the stop and attenuation. Okay, but now again, if we now make a deal, it's about the same deals what we did with the FIR filters. It's always you can control, or you can have either very good passband. If you allow some ripple, you get steeper filters. If you then allow some lower level of attenuation, then you again can squeeze the transition bandwidth shorter. So that's what happens on elliptic. So basically that's equal ripple on passband and stopband. Okay, and yeah, that's the history. So it's yeah.
So what does the equal mean? Equal ripple,
Equal ripple means a uniform ripple within the say +2 dB on passband, and then the stop band attenuation level. In that case, -60. Yeah, yeah, peaks at the same level. Yes. All right. So I already mentioned this one on the phases. So zero phase filter. That's just a one reminder that okay, if you really need to have the zero phase response, there is a way. So even with this nonlinear phase response filter, you can get a zero phase response by basically filtering the signal twice, first on forward direction, then on backward direction. And of course, only for post-processing. It's hard to reverse the time in real life. Believe me, I'm old enough to know it. I have tried and failed. Okay. But, yeah. For some reason, I also put some funny filters here. This is a kind of filter you can sometimes use even with, say, audio data. Median filter. It's basically you calculate instead of calculating the average, for example, or something like running average or weighted average, like in FIR, you basically calculate the median. So that's the center value of the sample. Okay, good example. So you calculate basically the center value of some region here and replace the rest of the signal with that one. So median filter basically is some sort of low pass filter, very nonlinear. The good thing actually about the median filter, and that's the reason why it's used so widely, if you have a sudden peak there, it disappears. You take median of, well, values like 1, 2, 3, 100, 4, 5, 6, 7. The median would be 5. 100 doesn't affect. Okay, the same thing for average. 113 divided by 8. So it's 20 some, around 20. Average would be around 20, but the median is just 5. So running average actually would do a bump here, while the median filter goes just like that. So if you have a speckle kind of noise in your data, that's your filter, meaning astronomy, or 2D. Dead pixels. Cameras has dead pixels. If you bigger the cell is, more probably it is you have a dead pixel there. How to get rid of that dead pixel? That's how you do it. Let's see, I have that one correct. So basically, the red dot there is that dead pixel, and basically we calculate the 3x3 median, which would be gray cell here. So that's the most frequent value. Right, and replace it. Ta-da, gone forever. All right. So that was the median filter. Matched filter, it's actually also kind of special filter used with all kinds of measurements. Basically, the idea is quite simple. If you know what you're looking for example, an echo of something, for example, echo cancellation on phone lines, right? You know what you are transmitting, so you can make actually a filter based on that one, or inverse filter based on that one, and remove anything that is reflected back. Okay, so fundamentally that's quite straightforward kind of thing. Or a radar, or acoustic radar, or that one. You measure snap, and then you can make a exact filter that passes only those frequencies through the system as you know they are. Anything else would be noise or artifacts. So that's the way to filter just this signal what you want to filter. Right. Woo! That was the theory part. About the exercise, I'll go through some of these with you, but anyways, let me